I, for one, I have a language of choice, like for example, for implementing my algorithms, but I absolutely do not deny any other one. It's just they're there for a reason and they should be used and they should be valued. And you should also value the people that use them because you're probably going to end up working with a person that knows a different language than yours.
The Inspiring Computing podcast is where computing meets the real world. This podcast aims to trigger your curiosity by talking to proficient and advanced users of MATLAB, Python, and Julia, who use these tools to deepen their understanding of the world, simulate, explore trade-offs, and gain insights that help companies add more value. In addition to this, we will also be talking to product marketing, toolbox authors, package developers, and library maintainers to see what drives the development and what issues they're solving for others to benefit from. Welcome to Inspiring Computing, Marcus.
Thank you.
It's great to have you here. I met you in Eindhoven, but you've got this wonderful profile as a YouTuber. You work at a company called Silks and Van der Lande. You've worked at ASML. You founded your own company. On the side, you're one of these super interesting guys that is just inspiring to talk to. But before we get into all of that, I would like to kind of ask you a little bit about who you are and how did you, as a Brazilian, end up in the Netherlands becoming a YouTuber. So tell me, what's your superhero origin story?
Oh, wow. Superhero. Yeah. Okay. Well, the story is quite interesting. So I come from a city called Fortaleza. It's a city very warm in the northeast part of Brazil. And it's a huge city. It's like a metropolis. I think it hosts 3 million people today. For my whole life, for the past 30 years of my life, I lived in the same place. I never moved out of my city. I come from a middle class family, normal parents, both doctors. One curious thing about my father is that he always wanted to do engineering and he could not. And this triggered me at the very beginning. He's an anesthesiologist, so he's the guy
Yeah.
that puts people to sleep. And he's good at he's really good at mathematics. He was a professor for mathematics, but it wasn't just profitable enough at this time. Then he became a doctor. So deep down in his heart, he wanted to do something technical, engineering, mathematics, but he could never because at that time, so in Brazil, it was a dictatorship back then. Wasn't a lot of stuff you could do. You couldn't be too creative. You had to go really streamlined. Then he became a doctor, also family pressure. And this triggered me. So I was lucky to have opportunities and go to school and just study. And I was also a very average guy. So I was never the top of the class. And I'm proud to say that. And the normal guys can do stuff like me. And it's also one of the drives I have to show people that things are possible. It's just a little bit change or a little bit perspective change that it's maybe a little bit of a push. So yeah, I ended up doing engineering because my father inspired me. He didn't do it. And I was curious to see why he wanted that so much that he always spoke about, and he would have like books and books of engineering and mathematics and difficult mathematical problems. But why was he a doctor and what not an engineer? And this triggered me into trying to see what this leads me to. And I loved the profession. I loved the academia. I loved the logical thinking. I loved everything about the way we should think, systems thinking, solving problems, putting problem, giving structure to problems, names to problems, putting the problems into blocks and connecting the problems and trying to find a solution. This is a very thing that I felt really in love to. And this led me to programming eventually.
But may I ask, well, what engineering did you then study? Oh, and this is in Fortaleza?
It was in Fortaleza. Yeah, it was in Fortaleza. So I did my bachelor's degree in electrical engineering in Fortaleza. So in Brazil, it's quite hard, right? It's a difficult country. You have to work a lot to earn there. And my family was already pressuring me to start working or making money or do this and that, just make my life work. And in this pressured me, this pushed me to try to find opportunities within my own academia degree. So eventually, for the first time in my life, I was given the opportunity to become a monitor. How do you call it in English? Is the guy, the tutor of a
Uh,
right? And that was a defining moment in my life because I was just doing like a test to see, okay, this is gonna give me a little bit money so I can just eat and go out with the friends. But I actually enjoyed it. I actually enjoyed teaching people how to solve problems in programming. And from that point forward, I always wanted to do something with programming. And this was in around 2012.
And what were you programming, if I may ask? Python, C, which language?
It was in C back then. So for some reason, they thought it was a good idea to teach C to electrical engineers. I think 1% of them actually use the language in their lives. And there was also, actually, it was C and assembly.
Oh, okay.
So even lower than C. And up until today, I don't think it's a really good idea to teach that lower level languages to that kind of profession. You could start a little bit higher, but
Mm.
I think there's a whole culture behind the choice of that language into departments. But I somehow I was able to do the test to become a tutor, and I absolutely loved to teach people how to program in that languages.
Okay, and so then but when you were teaching programming as an electrical engineer, is this where you already specialized? So electrical engineering, there's high current, low current, embedded systems, control, telecommunications. It kind of branches off into a wide variety of topics.
Yeah,
Did you focus on any area in particular?
yeah. At that time, so we were like in the first or second year. It was still too broad, so you could still have a lot of options. And I was slowly going towards something that had to do with programming. At that time, this became almost like a requirement for me to, okay, whatever I do, it has to do with programming because
Hmm.
I really felt in love with it. I would buy books to program microchips, so microcontrollers, so I could just blink lights and print hello words. I think I spent more than like, if you convert like $1,000 just in microcontrollers, different brands, just so I can just blink the LEDs because that was my hobby. It makes things move or blink. So it's there's something in programming that enables you to do stuff in the real world that makes me really like this. I like seeing stuff happening as I program whatever I'm trying to do. So this is really something that triggered me. Plus the teaching. So if I could teach people how to program so they can see stuff, LEDs blinking or motors moving or sensors being measured, and I can teach at the same time, this was like a perfect combo to me. I discovered my passion very, very early in my life.
So is that what kind of led you to your YouTube channel, Practical Software? Was that the initial spark in your life that said, "Oh, I like teaching so much. How do I teach a wider group of people? YouTube, here I come."
Yeah, absolutely. So there is so much stuff I learned with this platform that I couldn't just consume it. I should also produce something for people. So definitely YouTube is a really good platform. I can convey all the knowledge I have been gathering for many years. I want to make people see things so much simpler. It's something I really like doing all day.
Well, it's also, I guess, as you go through engineering, you learn a lot of theory, and it's maybe only later in electrical engineering that you start to connect the dots. And it's also somewhat unfair for high school teachers to be able to describe exactly what sensors are doing, how they work, the maths behind it, AC/DC converters, and all of these things. It's maybe an unrealistic ask to teachers who are already overwhelmed with the amount of stuff they've got to teach. Then you're kind of left up to your own means to figure it out. So you kind of figured out that programming is your thing. But then after university, what did you end up doing? I'm curious. Did you stay in Brazil? How did you find your way to Netherlands?
Oh, during my bachelor's degree, I still was connected to the university because I wanted to do a master's degree. There were not in Brazil, at least where I come from, so little opportunities for programming the languages that I liked, which is C++ and Python, that the best option I had was to keep in the master degree because then I could still use programming, do
Mm.
research, and try to look for really cool applications. So, and there was an open spot in my university that would also combine those things. They required someone with programming knowledge, with the MATLAB knowledge, with sensors knowledge, just general sensors, how to things work, control systems. So it also, they were needing someone like this to fill in a master degree scholarship. The research is highly underappreciated in Brazil and undervaluated. And back then it was still okay. Nowadays, not anymore. But yeah, there was a spot for me to be still in the master, do a master degree with the stuff I liked. And during the master degree, I first touched the topic of sensor fusion.
What was your master degree about?
It was about sensor fusion. So it used sensor fusion to best predict the motion of robots. So autonomous robots, AGVs. So my master's degree was about how to combine sensors to best estimate the location, the position of the robots based on the measurements, based on the constraints, and based on your robot model.
So when you say robots, is this kind of like for the RoboCup robots? These are like football robots, or is these walking robots? What type of robots are we talking about here?
Yeah, I wish I could show you a picture, but they were big. They were AGVs. They were as big as, yeah, as wide as a person. So you could say like 60 centimeters wide and 1 meter high,
Hmm.
visible. And they were supposed to be completely autonomous. So the idea of the master degree, the bigger topic, the umbrella topic that would guide the studies of many students were, how can we completely leave these robots alone in a room and have them do tasks?
Oh, I see. So this is like a household robot that would interact and pick up a can of Coke or put away things, wash the dishes, and you want to do this autonomously?
Yep.
Well, what sensors did you have at your disposal, or was your master thesis to decide which sensors was the absolute minimum at the cheapest price?
No, so luckily the cost was not the big problem that back then. The master degree, the master thesis was about, the goal was to locate your robot in a room. That is a very hard
Ah,
problem.
why is it so hard for a robot to know where it is? And what information and sensors did you have available?
That's already part of the problem. What kind of sensors do you need? That's the first question, right? So first you try to structure your problem. Where you have to answer the question where you are. So you have to model. The first thing you have to do, you have to model your motion. You have to model how your robot moves. Because if your robot has two wheels, it can't go sideways. If my robot cannot move sideways, it can only move forwards or backwards. There are places I know my robot is not. So this is part of the bigger problem, of the underlying problem of trying to locate where it is. Okay, good. So you have a model. Now you start putting sensors in the robot. Some of them are intuitive. What if I put a camera? Yeah, you can put a camera. What if I use the rotation of my motors with what we call encoders? Yeah, cool. We have encoders, we have a camera. Okay, what if someone pushes the robot in the direction of where it should not move? So where's the disturbance? Maybe we should put an accelerometer. Nice. What if the robot rotates, which it will? But if I cannot trust the wheels, if it slips in the floor, the wheels rotations will not tell its angular motion. Okay,
Hmm.
I put the gyroscope. Cool. Okay, nice. So it looks like a very solid robot at this point. Okay, what if it was to make it go outside? Like you can't trust your visual landmarks anymore. Everything is too far away. You cannot trust your depth. Okay, let's put a GPS. GPS is not precise. And so you start adding sensors to your robot and you put a number of them, but you will notice that every sensor has a deep limitation individually. Accelerometers are horrible for estimating a motion like positions and velocities. Horrible. They have a huge bias because of gravity and because of the nature of the MEMS principle of sensors. Gyroscopes has also nature inherited biases. The camera, yeah, the camera, it's difficult to tell. It gives you a very broad idea where things are. So you have visual landmarks, but you don't know how far they are. And there is the problem. How do I combine this number of sensors. We also added ultrasound sensors, so they act like a radar. How do I combine them nicely so that I have a really good position of my robot? The position is important because every task the robot has to do, the position is a must. If you're supposed to deliver a drone, if you're supposed to deliver payloads in the locations, you have to know with very high precision where your drone is. If your robot is a pick and place, so if it's supposed to pick a small a tool, put it there, it has to know exactly where it is. If one thing goes wrong in your estimation model, then the whole task is pointless.
So it's interesting. So already in your master degree, you kind of got exposed to this. So, but that was just you as a, I don't know, a 22-year-old who kind of figured all of this out. I would like to double click a little bit more on the sensor fusion, but I would like to double click not knowing what you know today, but knowing your journey for through the next steps in your career, right? So some of the things you're saying now, I'm assuming the 22-year-old version of yourself was like, yeah, well, how hard can this be? I mean, all these sensors, I'll be able to figure out within, I don't know, a couple of centimeters what can go wrong.
Yeah.
But I hear you speaking as now the more senior expert who's kind of like, well, so walk me through some of your next trajectories in life. And then we can go back into more details about the sensor fusion and the problems itself. Because I think that paints a picture of why you're saying the things you're saying.
So yeah, my master degree was about just learning about this problem. How do you write this mathematically? Because I have to prove stuff. I have to write a formula in my thesis stating what I'm trying to state. It has to be mathematically verified. It has to be correct. So during my master degree, I spent a lot of time learning about the problem. Every foundation has to be there. So there is a lot of probabilistics, a lot of linear algebra, matrices are involved. And I somehow had to program all this knowledge, all these algorithms. I had to program them in my robot. There was a computer there, and I had to program the things that I was learning in my classes in the robots. They wanted a person that would know how to program the things that we're learning in the papers and the books in the robots. So I was a really good match to test and perform experiments on the algorithms. I absolutely loved doing that part in my university times. I was the guy to go. So even myself, I was busy with this thesis, with the sensor fusion thesis, but I had a number of colleagues that would just ask me, hey, can you program this algorithm in the robot, please? Because I need to do experiments. So I would look at the formulas, it's just a summation. Okay, done. I will do it. He would just pay me a barbecue later on, and everything was already good and everything was settled. I was known to be the guy to program the models that they wanted to do in the robot. And if I knew it was too complicated, because 95% of our students were using MATLAB, if I knew there was a very complicated algorithm, I would simply connect the actuators of the robot to their models directly using APIs or some kind of interface. So they could just run their models in their laptops, and the robot would just behave as part of a small block of the plant. We call the plant. So the robot would just interact with their models in real time. I like connecting the theory part with the practical part a lot. So this made me a lot.
So maybe
I am today.
But maybe to take a step back, so you said something there interesting that maybe not everyone realizes. So most people think, okay, you program on a laptop, you have an idea, and then you give it to somebody else, and that somebody else reprograms the same thing, but something that a piece of embedded hardware can live with, be that a microcontroller, DSP, FPGA, depending on what your framework is. But you just said something there that in the development, if the algorithm is computationally expensive, and people are still discovering things, you were just connecting robots moving around and streaming data live from a robot to a computer. And then that would give someone who has got no skills in potentially programming a robot have the ability to understand, oh, okay, this accelerometer, it's not really giving me what I want, right? I turned and this is not exactly what I thought it would be. So my gyroscope is not so good.
Yeah.
So you actually, above and beyond developing programming robots, you're also thinking about APIs and testing, also at a young age, right? So this testing is a fundamental thing that But I don't think you formalized it when you were at university. That maybe came later,
Oh
I'm
yeah,
guessing.
no. No, back it was totally greenfields. Like we could do whatever we wanted. We didn't care anything about quality. That came later, like very late. And we paid the price. I don't want to say that this was okay. We paid the price for not giving quality to our algorithm or our code. We had students develop very fancy algorithms in C or C++ with absolutely no documentation, absolutely no information whatsoever, and they would leave the spots to do something else. Someone would have to pick up, and they would spend 6 months just to read 2 files. Would you believe that? 2 files of source code in C because it was so cryptic. It 2 files. I think in total like 1,000 lines. It's not much, but it was so cryptic that next students spent 6 months just trying to understand what it was.
So the concept of technical debt lives and breathes also at university. So
Yeah.
some people think that only appears when you come to commercial framework, but no.
At data, we felt like the worst. It was horrible. So over time, everything that happened, like this kind of stuff, everything made me a little bit more aware of what we should not do. Everything was a very good learning opportunity. My robot should have an API so people don't have to know about the robot so they can just test their algorithms. That's a very good learning. Or I have to document my code, or I have to write not things for people to understand, not to myself only. People to understand. It has to be teachable or understandable. So these were small steps that were slowly growing into me and became part of like my daily life today. So what I do today is just a summation of all these learnings of what not to do and what to do, lessons learned, and I just try to apply them all the time.
So maybe to zoom in, what is it that you actually do today? So I kind of said you work for a few companies, but I think on LinkedIn you call yourself a senior software designer or a software architect.
Yeah.
Walk me through where you work today, what you're doing, and then we can go back into the Sensor Fusion in a bit more details.
So nowadays I act as a software architect for a company called Siux here at Netherlands in Eindhoven. Siux is basically a software slash hardware company. So Siux makes devices out of scratch. Like if you just come to Siux and say, "Hey, I want a machine that analyzes semiconductor based chips that hosts laser reacting elements," they can do that. They know exactly the people to reach out and they bring up a team and they will make the machine for you. You just have to add very high level requirements. And moreover, Siux is also a company that offers consultancy, which is what I'm doing at the moment, for bigger companies here in the region, which is my case at the moment. So right now, I'm acting as an architect for another company called Vanderlande. Vanderlande is a huge company, worldwide company that basically sells logistics systems for everything that you can imagine. Amazon, UPS, DHL, PostNL, airports. If you see a conveyor belt in an airport, there's a very good chance that it comes from Vanderlande. And you can imagine those kind of systems and logistics, they run, you name it, software. So someone has to develop, maintain, test, apply DevOps, take care of, release new versions of softwares for those kind of logistics systems, which is what I'm doing at the moment for new products for Vanderlande.
I see. So that's where you're kind of coming from of talking about your university days. It's actually the same thing, maybe just on steroids and maybe formalizing it and trying to not make the same mistakes. Is that a fair assumption?
Yeah, you can say that because my colleagues come from different disciplines. I have colleagues working for embedded systems. It's a single product, like it's a single conveyor belt that do sortings, but they come from different disciplines. They come from PLC, so programmable logical controllers. They come from embedded systems. Some of them come from MATLAB, Word, so they come up with algorithms, and someone
Mhm.
has to plug those algorithms in the software that runs the sorter. So I am exactly in the middle of all this, of all these very excellent professionals from different multidisciplines, trying to make things work together. So right now I'm busy proposing interfaces, how is this controller should interact with the MATLAB model. There is an interface between. Those are separate entities. Someone has to design or generate or maintain an interface that allows the MATLAB model to communicate with the real system, with the real hardware and real equipment. Someone has to design an interface for this and that. So as an architect nowadays, I'm mostly busy with interfaces. I think it's almost a full-time job to just think, propose, maintain, make it really long, future-proof interfaces so your system is well communicating with internally and externally with our components.
I'm sure that you can spend a lot of time talking about what you do at Vanderlande. And it's interesting that maybe as a result, interfaces was not the first thing that your university professors told you when you said,
Well,
let's make the autonomous robot. But now you kind of see the importance of that and cross-team collaboration.
Yeah.
But maybe to kind of double click a little bit more on the sensor fusion, I also noticed that you have channels also about LiDAR, and you used to have a company, if I'm not mistaken, in Brazil, which used that. Do you want to kind of speak a little bit about that journey of leaving university, creating your own company? And can we zoom into that experience about telling me all the details of what is actually a LiDAR and how does it work and how is that actually solving all the issues you spoke about?
Oh yeah, that's basically everything that I love. All right. So back to sensor fusion. So I did my PhD thesis. It was fun. I met very cool professors that would really endorse my thesis. And by the way, the whole sensor fusion topic in my university was completely new. Nobody had touched it. So back then, my professors were busy with the control systems. So, for example, they wanted to control motors. Just an example. Someone has had to do measurements because you can only control what you measure, right? If you want your motor to run 60 RPMs, you have to measure the current speed. So what triggered me to go into sensor fusion, it was someone has to do good measurements. They had to give good measurements to the control system so that the control system could work well. So there was a big assumption in the department of electrical engineering that the sensors were just, it's just connecting signals. And I was there and they said, yeah, but that doesn't work for accelerometers. It works for simple motor speeds, but not for accelerometers. You have to filter those, not for gyroscopes. So it grew. It became a bigger thing in the department. And I later discovered when I was already in Netherlands and I went back to my professor for a visit, I discovered the sensor fusion group was big as 5 people already. It started
Wow.
me, my professor, we were the only ones, and now it has 5 people. And I would walk in the labs, people would look at me and say, "You're that guy, right?" Yeah, I think I am. So apparently a lot of stuff happened after I left. I was very happy to hear about this. But indeed, the main thing was that sensor fusion was lacking. We controlled systems, but nobody was measuring well sensors. And they would blame the controllers. No, your controller is not robust enough. It should be accounting for noisy measurements. I would say, no, you have to improve your measurements, not your controller. There was a particular, very interesting event that happened back in 2015. I was still in the master degree, studying all these fancy robot algorithms. We had a few colleagues doing exchange program in the US, and they ended up in Goddard Space Center, which is part of NASA. They did such a good work there with the professors from NASA and the engineers from NASA. They were supposed to reverse engineering a very old robot that was just not working. So we have a group of 3 Brazilians, my colleagues. They reversed engineering and documented the whole thing. So they completely overhauled the whole robot, made it work again. And the NASA engineer was like, "You guys are crazy. You should have this robot." The guy came out of the US to Fortaleza to do a speak. And in the end of his travels, he left the robot with us. And there was a very, very cool sensor in the robot, the LiDAR sensor. And then we discovered the LiDAR. If you're still on the topic of sensor fusion, right? You're still trying to solve the problem of where your robot is in your world. You have all the fancy sensors, And now we had a new one, the LiDAR. And the LiDAR is a sensor that gives you very, very good estimates on distances of objects in front of its field of view.
So how does it actually work? What does LiDAR stand for? And what is the basic physical principle behind it?
So you know radar, right? So while radar is based echoing, so it's time of flight of radio signals, LiDARs, they send laser signals to the objects, and based on the time of flight, they do estimates of distances. So it's the principle of echoing. So the underlying physical principle is time of flight. So the lasers bounces off surfaces or objects, and because we know the speed of light and we know when we shoot the signal and when we get the signal, we are able to calculate the difference of time of flight, and then we can tell how far away the object is. It's the same principle of the radar. It's light detection and ranging.
So, okay, so now you have this LiDAR, right? It's not like a laser pointing in a single direction, right? LiDARs, they're moving around, they're spinning around, correct?
Correct. There are variations of LiDARs, but the principle is the same. Like you shoot a laser and you get back the distance of objects, but you do have variations. So we have LiDARs in 2 dimensions. They sweep a plane.
Mm-hmm.
So in 2 dimensions, you have a sweep plane. Usually they come with degrees. So you have like 90-degree LiDARs. They look at everything in 90 degrees field of view. We work with 180 degrees LiDARs. So they sweep the whole field of view in front of you, for example. And also 360 degrees LiDARs. In the past few years, they started developing 3-dimensional LiDARs. So not only it sweeps a plane, in 2-dimensional plane, it sweeps also an angle in 3 dimensions. So it's basically just a plane. If you would angle up a plane, you have already 3 dimensions. So there you have it.
So, okay, so you had this LiDAR, right? Coming back from your
Yeah.
friends from NASA. They gave you a LiDAR, and this was new. So now we know what a LiDAR is. So walk me through. So is this something you just put on top of your robot and magically you have what? An array of distances? Is that how I should imagine it? So your output of a LiDAR is just one big array of saying, okay, in this angle, I have an obstacle within X centimeters, meters to a certain degree of certainty. Is that how I should think of it?
What it does, it sweeps a field of view, either three-dimension or 3 dimensions. So you get a sweep, and you get you get indeed an array of distances and angles. So you know exactly where the ray was pointed and how far it went. And you have a number of them. This, depending on the LiDAR, you can have up to 100,000 points per second being measured. Very fancy LiDARs can scan up to 2 million points per second. That's a lot of data per second.
Mm.
And they can be also all sorts of precision variations. We can have LiDARs as precise as 2 centimeters, as precise as 1 millimeter.
Okay, so now you've got this LiDAR. So the one that you got from NASA. So I'm guessing even if it was 2 centimeters, that was probably what you were very happy with. But you mentioned early on, each sensor's got a few gotchas. So where do LiDARs fail? What is their gotcha?
So if you want to, for example, 360-degree LiDAR, the price goes off the charts. It goes way up to the point that you start questioning your own project. Okay, that's not feasible anymore. So you have to work with low-cost LiDARs, and low-cost LiDARs have low field of view and low distances. At least from our projects where we used to work, it was never the case that we could acquire a very fancy LiDAR. It would solve a lot of problems, but it was just too expensive. This was a good thing because this made us propose really good sensor fusion algorithms because it was able to handle constrained models. The LiDARs were okay. It's okay not to have such a good high field of view, but even if it's like 60 degrees, we were able to model all these limitations and combine with different sensors to still have a really good estimate on the robot's location. And yes, the LiDAR was on the top of the robot. It would look frontwards. it would do sweeps in 180 degrees. You still need to see what's happened behind you or right next to you. What if a person walks in front of it? Is it part of the scene or is it noise? What kind of algorithm
Mm.
do you develop to filter dynamic information? What kind of assumptions do you have to make? What if there's a gas or the clouds of dust? Because it also captures those. So the algorithms needed to be robust to handle those kind of situations, all the different noises. And this is where the fusion also brightens because you could develop an algorithm that would detect that the sensor was not trustworthy anymore. There are algorithms that looks at the data of your sensors and are able to tell you, oh, this is not, you don't have to, you cannot trust this. The covariance is too high. The uncertainty is too high. Switch back or smoothly switch back to another kind of estimate. Okay, let's look at the camera now. The camera looks okay. So there were heuristics to tell you how trustworthy that your sensors could be. And the lights
Ah, so,
were usually the good ones, but they're still susceptible to dynamic scenario changes.
so you said something kind of important there that I want to double click on. Intuitively, you might think that I've got all these sensors, so they're time stamped, so you know exactly when each data comes, right? So it's all running off a certain clock, and maybe they're running some faster than others, which
Yeah.
is problem number one is okay, so my LiDAR works at a frame rate, my camera's running at another one, and my ultrasound at another one, my gyroscope has got another. So there's some kind of assumptions going into place, but you probably can align it with some relatively simple maths, all the data at the same time. But that's at a static moment. And the idea is to create a virtual map of where you are. And as you're moving around, that map gets better defined. Or is it the fact that you say, well, actually, in this situation, I don't need all of my sensors at once. I rely on these three, but I've got redundancy programmed in. And a bit like if you're going to space, there's a whole bunch of systems which have got redundancy in. Is that the same thing that is happening with sensor fusion, that you're, even though you've got more information than you need, you optimize for the least amount of information to get the best position? Is that how it works?
Yeah, more or less. So sensor fusion is a little bit simpler than what you just described. So it's a building block before that. So the sensor fusion is more about the capture and the modeling of the sensors for some purpose. It's very often the case that the purpose is to build a map. So the end
Mm,
goal was to build a map. That being the case, indeed, there are algorithms that are based on probabilistic maps that makes sure that, okay, if this laser, for example, very simple example, let's say your robot stands still and your LiDAR is pointing to the same thing multiple times. So it has already, I don't know, 20,000 samples, and every sample, the point is the same.
mm,
We implemented algorithms that we call grid mapping that relies on the fact that, okay, if this happens that often, this point is part of the map. You can really statically assign this position
right.
as part of the map. If noises are coming back and forth, people are walking or dust comes, your sample at that specific point in space will not happen as often as a static part of the scene will happen. So it doesn't get assigned to the map that easily. It's a probabilistic model. It's based on
Mm.
Bayes updates.
Okay, so there's a whole bunch of maths around this. So if I go back to the sensors itself, and talking of robots, you spoke about C++ and Python. Did you, by any chance, be using the robotic operating system, ROS? Was this also what we're using to stream data, or am I naively thinking you adopted ROS in
Oh,
this project?
no. We did use ROS, yes. We use ROS a lot. So turned out during our studies, we went to a lot of conferences all the time to publish papers, to watch other people doing their papers. It was very often that people would publish papers and they would mention ROS as the framework that they would use to produce experiments. Why? Because ROS, it gives you a really good foundation to write drivers. So you could very easily write drivers in C++ or Python that would get the raw data from your sensors and publish it in a node communication paradigm. The principle is quite simple. You have topics and nodes. Nodes are processing units, aka a driver, for example. Every time the driver would talk to a real sensor or using a piece of software that would talks to the sensor, get the data out of the driver, it would publish to what we call topic. And the way ROS works is you can have multiple nodes subscribing to the same topic, which is basically a stream. And every time you would publish new data or your camera would publish new data, you would have a process that was listening to this information and you could use this. And it was really good because ROS solves a lot of common problems, a lot of patterns that you really don't want to spend too much time on. You don't want to care about timestamps, for example. It solves for you. It assigns the correct timestamps based on some small assumptions. Okay, this is roughly synchronized, so let's use this timestamps. It solves the messaging, the bus messaging information. It also queues. It solves a lot of problems that you spend so many hours, and these is really common problems. So it gets you to the point. Okay, I have I have a sensor and I want to get this sensor information. You would write very easily a driver to get this information and use it. So many people use ROS that there were drivers for absolutely everything. So at some point, we would only buy sensors that wouldn't have ROS drivers at university.
So maybe just for those who don't really know what ROS is. So it says robotics operating system, but is it really an operating system or is it just a framework on top of embedded Linux where you have a mechanism? It's basically like a message protocol that connects hardware to different clients. You call them nodes and topics. And those can be on the machine itself or off the machine. Is that kind of how you were specifying your API towards, I don't know, MATLAB or Python back in the
For
day that
example,
you were like communicating?
for
Is that?
example, yes, it's definitely not an operating system. I think if you open the page of the landing page of the ROS, it tries to disclaim that it's not an operating system. It is indeed a framework. So it's basically building blocks to build your own software, your own applications with all those reusable patterns that we are. So it's very convenient for robot applications. That's why it's called robot, because for robots, it makes a lot of sense. And a very good thing about ROS is that it really abstracts away, even on the machine level. What do I mean? I mean that if I write a driver in my Raspberry Pi and I post the information for an accelerometer to a topic, any other machine in the same IP sub-range can subscribe to the topic, and ROS automatically figures out all the networking for you.
Mm,
So you can have multiple devices publishing multiple data from to different topics, but you don't see this. You just subscribe to the topics and the data comes magically and you can already use it. Thus, we could have very high performance computers running MATLAB, and the MATLAB application would subscribe to ROS topics coming from the actual hardware sensors. They would have
right.
the correct timestamps, everything was already done, so they could really run their algorithm as if they were running in real time. It's really, really cool.
So my understanding is MATLAB does it, but also Python is well known for having clients who could also parse that. And if I'm not mistaken, the visualization then becomes a really important thing, right? One thing is getting a bunch of numbers like a LiDAR and you get thousands of numbers and now you need to present it in something more visually understanding.
Yeah.
Then I think there's also simulators that can rely on that. Is that true?
Correct. And also part of the ROS framework is to provide all the visual interfaces that you would need usually for robot applications. So I could very easily, and they behave exactly as any other node. Like if I
Yeah.
have a node that runs a driver publishing data, I can have a node, a 3D application subscribing to the node and just rendering all this information in 3 dimensions in real time for me. I use this a lot because for 3 dimension navigation for robots, it can get very hard and non-intuitive real quick unless you
Yeah.
have some kind of visualization tool. Another very cool thing about the ROS is that you could literally store every information coming from everywhere in a single file, and you can replay this in the future. And this was very important for my company. My company came out of, instead of having robots do three dimension maps? What if a person just carries a robot with the LiDAR, with the same equipment, with the same sensor fusion algorithm that builds the maps for robots? What if the person just walks with the stuff?
Yeah.
And it worked. So it was just a portable laser scanning device that would use ROS and all those things that I learned in university.
But then maybe just to double click before we get to your company. So Rust sounds super cool, but it's not perfect, right? So it has limitations. I can imagine there's tremendous amounts of data going from left to right to that. But then I guess you start losing some of your real-time guarantees, which
Yeah.
I guess your control engineers live and breathe and say, no, I need to have deterministic real time. And I guess Rust has also evolved over time. So maybe when you were back at university, it was Rust version 1, and now there's a V2, and
Mhm.
there's additions to it. But it's not that the whole world works on top of Rust, right? You do not have to use Rust for robotics, but it just so happens that that is one of the common frameworks. Is that a fair?
Correct. Yes. So it turns out for a university for research, it's very convenient because you don't need that real time performance at all most of the time. So indeed, the limitations of ROS are, and they're trying to mitigate this in ROS 2, exactly that. So real-time performance. How can I guarantee that the time my sensor data is published? What if I just have a pointer to the data instead of
Hmm.
serializing and deserializing? ROS tries to solve this with plugins and also fancy constructs. But then you start thinking, okay, I'm basically almost writing a code to Performatic, and the framework it's just a small part of nowadays.
Yeah.
I want my application to run fast. I want the monolithic application. I don't want the distributed application anymore. And then you start thinking, oh, maybe ROS is not the thing for me. But for experiments, it's definitely an option. But
So there's a trade-off there, right? Experimentation versus quick results, proof of concepts.
yeah,
If you go to a well-defined system, maybe such as some of the companies that you worked in the past, then maybe it's not as common to find that ROS being there because you have to work with more deterministic things. At this moment, you're at a much more secure place of what algorithms you want and what to expect. Talk to me a little bit about testing. Does testing become much easier with ROS, or how do you actually do testing with sensor fusion in the first place? I have this mental model that you get mammoth amount of data, great, you can store it, but it's very much depending on the time of the day, the gravity field, if it was dusty, a floor, or all of these variations feels like it can change these numbers dramatically. So how do you actually test for this? Or is it trial and error and we just keep banging our heads until we get it right?
so yeah, turns out in university there was a lot of trial and error. ROS enabled us to really capture our experiments. So that was a very good thing. So that's one of the best things it had at the time was to capture our experiments to the tiniest degree. So no data was lost whatsoever. And we could replay the same. It stores the timestamps. It stores everything. It knows exactly the sequence of when the data was posted. So where you would replay your experiments, you could hook up a better version of your algorithm and see if your map is suddenly better.
Yeah.
The problem is, what is a what is the truth? We don't know. We can only guess. And the hardest part about sensor fusion, at least for mapping, right? For mapping applications, it is to find a solid sense ground truth data. It's very hard. It People have it. So you could download from datasets, Kitty datasets or other datasets, very famous datasets for this kind of application. But they only have a single scenario. So the largest data set we have to validate sensor fusion algorithms, I think we have 2 or 3 options because it was so much effort to generate a ground truth information.
Mm.
There's not many of them. And okay, but my experiment, what I can generate in my own lab is never going to be the same. Is a different ground truth. How do I generate the ground truth out of what I have, not work from a database? So that is
Yeah.
really hard. It was really hard to tell, hey, my algorithm is better. And the peer review researcher would say, okay, did you test against the Kitty data set? And I would say, no, I tested against this other data set. And he would say, then how do I know if it works? Yeah, but it's a different scenario. The Kitty data set is trying to solve autonomous driving. I'm trying to solve a different problem. And then the discussion arises, okay, where's the ground truth? So
Yeah.
in our every experiment, we had to, to the best effort possible, provide that we measured our sensor fusion outcome. We had to provide a methodology that tells us this data is correct. So usually we did hand measurements with another equipment,
Validate.
a terrestrial laser scanner, to build a map, like a ground truth map. And then we store this, and then we call this is a ground truth. This is the latest equipment that I used to generate my ground truth. It's a certified equipment. It's very expensive. We rented that. It was very expensive, but we generate the ground truth. Okay, now I can run my algorithm and I can test my data against the ground truth. But it was very hard to generate the ground truth.
But then if you can build a machinery that can match the ground truth, shouldn't that machinery then itself become the cheaper version of measuring the ground truth in the first place?
That is what I made a company for, because at some point our fusion was so close to it that I spoke to a partner in my university and we thought, hey, I think we're ready to go to the market because it's almost the same. But this was a pitfall, huh?
So tell me a little bit about the company you created and what was the pitfall that you encountered.
So turns out, and this happened right after my master thesis. So I was already in the PhD now at this point. So me and another colleague, another master student, saw in our results that the results were really close to the ground truth. It was very close. And we immediately, naively thought, hey, we're ready. We should make a company out of this because it's the same thing. This equipment, the ground truth generating equipment, would cost 600,000 reais, which is $100,000. And the lasers we used in the university were like $10,000 or 2,000 reais. It's like 100-to-1 relationship. And we would generate the same data set. So very naively, we thought, this is good. We should sell this thing. And then all our premise, all our business model, everything that we tried to sell was based on that assumption. Hey, it's the same thing. And then the company came to be, right? So we went to families, we asked for money, we went for the government, asked for money, they gave us. So we were very convincing. Hey, look at the ground truth, look at our system. It's really good. Buy us. This was the thing. And we were really good at selling. We hired marketing people to add very fancy landing pages. It's still up, it's still online, I think. Very fancy landing pages, and they would see GIFs and animations and videos of our system capturing the three things and the ground truth right next to it. But pitfall, our equipment was very well tuned for the ground truth. It was biased. It's stupid for a scientist to think that was not biased. It was biased. We were young and stupid, I would say. And we did not receive enough critics from our professors or for people saying, hey, you should test this in a different scenario. Like more similar to what the market needs. Our scenarios were really just research scenarios. They were like laboratories, they were parking garages, they were warehouses. Those are really easy to capture the ground truth from.
And then what? You took it into a art gallery and then you started getting refractions and things like that. Oh, dear me.
So one of our customers, over time, we evolved. We ended up creating a physical hardware device. You could hold it with 2 hands and point it to stuff. It would generate it 3D. It was really cool. But our customers' scenarios were absolutely different. People would walk in front of the equipment and you could not tell them not to walk because it was part of a construction site. The customer wanted me to capture the construction site progress, but he would never allow me to make people stop. I spent so much time manually removing people from my 3D point clouds so that it's closer to what I wanted to capture. But the person walking in front of the equipment introduced a noise in my measurements. It was not part of my model. I was not expecting. Everything in the laboratory is static.
Controllable.
Very naive. I understand. It's very naive. I was also very optimistic. I was hoping that the market would have as much easy, happy flow scenarios as I would have in the laboratory, but it was never the case. I should have
Right.
asked immediately, okay, what is the market looks like? What is the
Yeah.
ground truth of the market? Not the research lab, the market. What is people trying to capture? Oh, they're trying to capture buildings, like very high buildings, because they don't want people to risk themselves trying to measure stuff in the buildings. They want the latest.
To do it from the ground.
That's a very good use case that we just learned so much later.
So you say maybe like a silly mistake, but I call that experience, right? So as we age, you go through these, and I think you stated very clearly and nicely that what you're doing today is a summation of all the things that you've learned. And also, from what I can tell, that's exactly what your YouTube channel is all about, right? You're sharing, teaching people that without them having to go through the same journey as you, maybe you can shortcut and make humankind a little bit more knowledgeable. Because some of these things, the way you articulate them, it's just like, yeah, well, how hard can it be? You say you're the average guy, but I would debate that highly. But it is easy to forget some of these things when you're in the zone, right? And you're focused on something and your heart believes in it. And it's like, of course the table's going to be stationary. Why would the table move? Why would anyone walk in front of the table? I don't have a cat. Well, why would there be a cat there in the first place? Who decided to put a cat here? So I can understand that real life kicks in there. Marks, I think it's very cool. But can you maybe tell me a little bit more about your YouTube site? So I'm kind of curious now. Is this kind of what your YouTube is all about, that you're just trying to teach people, or are you trying to solidify your own understanding of the world by teaching others? Tell me a little bit more of the driver of what was behind this YouTube channel that you've got going.
It turns out like a little bit, the YouTube started as my company is ending, right? So it's still a progress. Everything is all right. A lot of things happened at the same time during my leave of the company, right? So there was back last year for the whole year, I always worked in a company in the Netherlands for a full-time job, 8 hours a day. But for my whole year last year, off work hours, I would give attention to my company in Brazil, trying to solve all these complicated problems with the scanning, having people go inside and try to make measurements. And so for a whole year, I was trying to make it work still.
Hmm.
And I just simply could not. So the fact that I moved to the Netherlands and my company stayed in Brazil, it made my life so hard. But I learned, like you said, I learned so much also in this process. Turns out, after this period, that my company is just phasing out of the market, that I felt a very deep need to do something. Like I should keep doing something. I can't just live like this. It should go. It should mean something. And over the years, I also accumulated a very high need to somehow keep teaching people. So in the university, I did it a lot. So while I was doing research, I did a lot of teaching there. So I was almost an assistant professor. People would confuse me as for the professor sometimes because I really enjoyed what I did, researching and teaching. So when I started the company, this was a little bit as left for side. It wasn't as much given attention as I wanted to. So as soon as the company, I finished with the company, I had a sudden urge to go back to this teaching part that I always enjoyed, even from the beginning when I was teaching people how to program. And then I had the idea. I already used YouTube. I think it's a great platform. There are so many great channels there that teaches intuitiveness and rediscovery. So I ended up compiling a bunch of YouTube references that I enjoyed. I compiled my past experiences. I compiled it's basically a compilation of what is the result? What is the outcome? What should come out of me? I know I work, I know I do this and that, but what is the legacy or what is the thing that will last? Because honestly, I don't think what I do in the companies in the Netherlands, I do work, but it's just something. It's not permanent. And I felt a really high need to do something that is more permanent, that is like something that
Mm.
will stay, that will linger, is really teaching, is really experiencing, is really trying to make people think and rediscover concepts that, and then I create a channel, and the channel is called Practical Software.
Go
It
ahead.
is an
Yeah.
attempt to summarize everything I enjoyed and everything I think people would also enjoy learning.
So I think your YouTube channel is super cool. Just out of curiosity, for those who want to reach out to you and learn more of everything that we've discussed here, what would be the right way to reach out to you?
Yeah, I do read LinkedIn messages and email and Instagram. So those are the top three. YouTube, yeah, of course,
Okay.
YouTube as well. If you can rank them, I would say YouTube, Instagram, LinkedIn, and email.
So you have used MATLAB, you've used Simulink, you've used Python, C, C++, and program embedded devices. You actually have a good overview of different technologies, but often people don't cross as many borders and they tend to zoom in on one environment and forget about the rest. Could you share some insights that you've picked up along the way around MATLAB, Python, and C++? Some of the good and the bad and the ugly?
I started with C and C++. So this is what I learned from the beginning. And up to this day, C++ is my go-to language. But I think there's always a context behind your choice. That's reasoning. And in my case, the C++ was the language to go because I all my life, I touched so often with hardware and high performance and drivers and sensors that it was and still is the language that makes more sense to me. So I like having an easy interface with my machine because this is
Okay.
what I want to do. I don't want too much abstraction because of the stuff I do. It's really talking to machines. I talk to drivers. I talk to chips. I talk to sensors. So for me, it makes a lot of sense in C++. But I do recognize the value of each individual language, right? So they are there to serve a different purpose. And I think it's fair and wise to acknowledge that they do serve their own purposes. For example, in my company, I have a multidisciplinary team. One of them uses structured text for ladder programming. It's a horrible language and they know it, but it's the best language for the task. You have to be aware of this. You just have to leverage and recognize and acknowledge that the language, it's not up to you. It's up to your solution. More about the
Mm.
solution than yourself. Over time, I did accumulate experiences, so I can tell a very nice examples of where Python was really nice. For example, for testing, is really nice. Which even for testing embedded systems, we use Python very often because it's a language that is easy to talk to the test engineers. You could show them scripts and you could show them your test cases, and they would understand it. Whereas in C, not as much. MATLAB is a really good language to model problems, to try to experiment and have like a free playground. Look at the build up matrices, invert the matrices, or computer determinants. So it's really close to algebra. It's really close to mathematics and physics. So it's a really good language to start. And for one, I have a language of choice, like for example, for implementing my algorithms, but I absolutely do not deny any other one. It's just they're there for a reason and they should be used and they should be valued. And you should also value the people that use them because you're probably going to end up working with a person that knows a different language than yours. And maybe it's the same project.
Right. Yeah. That's the real world. So and maybe back in the university days, your professor could control everything, but the real world and larger projects, that might not actually be the case.
Yeah.
So I like that, respecting language diversity. That's it for today's episode. I hope you enjoyed the conversation and found it valuable. If you did, please consider sharing this episode with your friends and family or anyone who might benefit from it. Also, I'd love to hear your thoughts, so take a moment to leave a review and let me know what you think. And if you haven't already, don't forget to give us a rating. It really helps us reach more people and bring you even more amazing content. Thanks for tuning in, and I'll catch you on the next episode.